Okay, guys, happy Friday. Uh, so hopefully Williams has gone over the homework with you guys. I'm going to talk a little bit about or finish up the notes from yesterday a little bit, and then talk about Half-Life, and hope you guys have a good weekend. So let's get started here. So where we kind of left off, and I may have to, I probably had my, yeah, I got it. Had this open, but we left off in the middle of the nuclear transformations that we were talking about here. Let me get down to the last couple of them quickly. Sorry about this. It kind of depends on where we were, which class, but we kind of stopped here with boron 12, or we got to boron 12, I think, in all the classes. So I'm going to go on to the next one. If we already did this one with you, that's fine. I'm not going to spend a lot of time on them. But there were like 2 or 3 more that I was going to go over with you, and then I was going to ask you to do a few of them, and I'll show you the answers. But here, U-234, U-234 will alpha emit. It's greater than 83. So here's U-234, 92, undergoes alpha emission. So that would be He42. And then I would need to add the product, which would be 230 and 90, which I believe is thorium. Thorium is not always the one that is decayed with uranium. Well, not thorium-230, but thorium would be, because it's going to undergo alpha. Likely that it would undergo other types of radiation as well, or other particles would be given off. But for the chart purposes, all we're dealing with is just the one alpha particle. In the next one, arsenic-74, I think we got to this in one of the classes, but arsenic-74 here, 33 down below. This would give you an odd situation. We're not over 83, so up at the top, are there more protons than neutrons? No, there are actually more neutrons than protons. This is, I think, 41 neutrons and 33 down here protons. It's a plus. So this would be odd. Is it any of these? It is not, so it's unstable. So the atomic number is greater than 83. If I go over here, is the mass of the isotope less or more than that on the periodic table? The actual periodic table mass is 75, so it's going to be less than. So we'll go down this way, and we can choose to do positron emission or electron capture. Let's go ahead and do electron capture, because that gave my my 6th period kids a little bit of fits. But here, 33 minus 1 is going to end up being 32, and then 74 on top. If you look up what element 32 is, what is 32? It is that right, germanium? Did I do this right? 33 minus 1 is 32, yeah. So it'd be germanium. I don't remember doing that, but okay. Yeah, so electron capture would actually capture an electron and essentially change a proton to a neutron. All right, so let's go look at the next one. Oh, no, it's your turn. So there's 3, even though I asked you to do a couple yesterday. Go ahead and try these 3. I'll ask that that Williams just push pause and wait, and then I'll show you guys what the actual answers are here in a second and go through them with you. So go ahead and give them about 3 or 4 minutes to try these 3. Okay, so hopefully you've tried those 3. Here are the answers for those. Whoa, wow, that's a mess. Look at that nonsense. So here are these 3 right here. The radium-226 is going to decay by alpha particle because its atomic number is 88. You would have found these on the periodic table. 88, fluorine is 9. Selenium, of course, is 34. And then you would have gone through the chart and figured them out. If it's positron emission or electron capture, you can just write one of those 2 down. And so if you guys are going to check these, again, you can press pause and let them check these real quickly, and I'll come back. Okay, so you checked those. Nuclear transformations is pretty much what we've already done. However, if you have 2 atoms and you slam them together, you can get multiple products, and that's kind of what we're talking about. This is what happens in super colliders or in the cyclotron at A&M. New particles could actually be produced. This is what Dr. Augustessian studied that I was so fascinated with, I talked about yesterday. But during a nuclear transformation, a stable arrangement causes those proton and neutrons to change, and you can end up with something that is less stable. And so we'll show a few of these, but really what you're doing is just balancing equations. So if you bombard something with an alpha particle or you expose it to alpha particles, so say you have stable nitrogen, that's nitrogen 14. And when I say bombard, you're going to expose nitrogen to something that gives off alpha particles, like, I don't know, uranium would be fine. And what you get as a product from that nitrogen is these over here. Now, you don't have to predict what those are going to be. It's not like the chart. We're going to tell you what they are. You're just going to balance them, which is really pretty easy. Something else you can do or is possible is bombarding with neutron particles. This actually happens in a nuclear facility or in a nuclear power plant. You use U-235 or U-238. I think it's U-235 though, but anyway, uranium, and uranium gives off neutrons. Those neutrons then hit other uranium atoms and cause a chain reaction. That chain reaction we'll talk about later, but it heats up water and you can use it to turn a generator, or heat up water, boil the water, the steam turns a generator and produces electricity. So really all nuclear energy is making electricity, making heat really. But anyway, that's another way you can do that, is by bombarding with neutron particles. So that takes us to talk about what we needed to talk about today, which is half-life. The half-life is the amount of time it takes for half of something that is radioactive to decay to some product, usually a more stable product. So it's the time for half of the atoms to decay to products, right? And it's going to emit some type of radiation. For our purposes, we're really not going to talk about the equations for these. We're just going to do the math behind it, but it's really simple and really short. The longer the half-life, the more stable that isotope. So if something has a half-life of just a few seconds or even fraction of a second, it is crazy radioactive. Something that is longer half-life would be more stable than something that's shorter. Now, that doesn't mean that having something longer with a long half-life you would want necessarily like in your body, because it would be undergoing radiation for an extended period of time. If you were using a radioisotope for medical purposes, you would want something that had a really short half-life, so it's not in your body as a radioactive decaying substance for a long time. But anyway, they follow a first order rate law. For you guys, that just means there's a rate associated with them. And the way to calculate it here is the amount remaining, that means your remaining amount, equals whatever your initial amount is times 1/2 raised to the number of half-lives. So you can figure out the number of half-lives if you know how long one half-life is and what the total time is. And we're going to do a couple of examples of these, and maybe a couple of them you guys can do on your own. So here kind of shows you the first order kinetics of half-lives. If our concentration or our percent is over on the left-hand side as the sample remaining, as it goes down, as that reactant decreases, it decreases by, like, if this is one half-life, it decreases from 100 to 50, which means there's 50% of it left. Or if I started with 100 grams, I'd have 50 grams. After a second half-life, they're undergo another half-life, and so I would have half that amount, which is about 25 grams. After the third half-life, I have about 12.5 grams, and after 4 half-lives, so forth, 0.625 or whatever. You can figure that out, but half of them will decay to a stable isotope. So it says there's 12.5 grams remaining, or 12.5% remaining. How many half-lives took place? Well, it went from 100% to 50% to 25% to 12.5%, which means 1, 2, 3 half-lives. All I did was divide it by 2, 3 times to find out how many half-lives. Pretty easy. Could have used the graph, of course. It even says to use the graph, but whatever. You can do it that way as well to find out how you get to 12.5%. So let's do a couple of examples here. Let's do this first one. So it says you start with 2 grams of nitrogen. So that's your initial amount. That's what you're going to start with, is 2.00 grams. I'm going to show you a couple of different ways to do this. 2.00 grams. How many grams will remain after 4 half-lives? So what you're trying to find here is your amount remaining, which would be your remaining amount equals your initial amount times 1/2 raised to the n. So they want to know my remaining amount. My initial amount was 2.00 grams times 1/2, and they said the half-lives were 4. That's it. So you would do, 2 times, what is that, 1/16? 1/2 to the 4th power. And you could do this totally in your calculator and you get an answer. I forget what it is. However, If there's 4 half-lives that took place and I start with 2 grams, so that's one way to do it with the math. The other way to do it is 2 grams under 1 half-life, or after 1 half-life, it would have 1 gram remaining. After 2, it'd have 0.50 grams remaining. After 3, it would have 0.25 grams remaining. And after the 4th one, it would have 0.125 grams remaining. That is 1, 2, 3, 4 half-lives. The answer is yeah, you can solve it that way if you want to. You could do the 2 times 1/2 raised to the 4th power, or you could just divide it by 2 4 times. So here, for this example number 9, phosphorus 32 has a half-life of 14.3 years. That's how long it takes. How many grams remain after 57.2 years from a 4-gram sample? So I'm going to let Williams choose. Hey, if you want to let them try this one, if they're game, let them take a shot, or you can hit pause, or you can just listen to me go. Okay, so either you're letting me show you, or you're still on pause. Anyway, whatever. Phosphorus 32 has a half-life of 14.3 years, and it says that I have a total time of 57.2 years. So I'm going to divide that by 14.3. Well, how many is that? I think it's 4. So, and then it says from a 4-gram sample. So if I started with a 4-gram sample and I knew I underwent 57.2 years divided by 14.3, I believe it is 4. It underwent 4 half-lives. I could just divide it by 2 4 times. So 4 would be 2, then it would be 1, then it would be 0.5. Let's see how many half-lives is that? 2, 3, and the last one would be 0.25. And so that would be 4 half-lives. It says how many grams remain after that amount of time. Well, I knew 4 half-lives took place, so I divided by 2 4 times. It will be 0.25 grams remain from the 4-gram sample. Pretty easy to do. If you didn't want to do it that way, you could certainly do it the other way. You had a 4.0 gram sample multiplied times 1/2 raised to the 4. That will give you your remaining amount, in which case you should get 0.25. And then the last one, I do want you guys to give it a shot. It says a 15.5 gram sample of nitrogen-13 decays to carbon-13 with a half-life of 10 minutes. How many grams of N13 remain after 12.2 hours? Why don't you guys give that one a shot and then come back on and I'll show you how to do it. Okay, so hopefully we're at the same page here. 15.5 gram sample of nitrogen-13 decays to carbon-13, half-life of 10 minutes. And they told me the total amount of time. Oh man, hopefully the announcements are over now. So you've got 12.2 hours, but each half-life is 10 minutes. You need to find how many half-lives in order to use the formula. Or you need to know how many half-lives took place in order for you to divide it by 2 however many times. So let's go find out how much time that is, or how many half-lives took place. It says 12.2 hours, right? I need to change that to minutes since each half-life is 10 minutes. So let's see, 60 hours is a minute, call it. 1 hour is 60 minutes. Man, sorry about that. Apparently Zon is having Anchor in her room, 1232. Okay, so 12.2 hours times 60 minutes. So this would be 732 minutes of total time. If I divide that by 10 minutes for each half-life, I find out the number of half-lives is 73.2 half-lives. Okay, you're not going to be able to divide something by 73.2 times. So you'll actually have to use the formula. The original amount, I believe, was 15.5 grams. I'm going to multiply that times 1/2 raised to the 73.2. If you put that in your calculator, hopefully you guys got 1.43 times 10 to the negative 20. Ran out of room. Oh, well, let's rewrite that. 1.43 times 10 to the negative 21 grams. So most of the easy ones, you'll just be able to divide by 2 like we did on the first 2. But if it's not one of those super easy ones, you may have to use the formula. So the amount remaining will equal your original amount times 1/2 raised to the number of half-lives that you have. So last couple of things to discuss. One is a decay series, and we talked, I talked, depending on the class period, a little bit about this yesterday. but it's a series of decays that eventually lead to a completely stable product. So they may actually have several steps. The most famous of this that's found in most textbooks is the U238 decay series. What you start with at the beginning is called the parent, and then what you get from each one of the decays is called a daughter. So you, excuse me, so you have a parent nuclide with different daughter nuclides as you go down through the series. So I'll show you, and it eventually decays to solid lead. But if you look at this picture here, let me get my pen to be a little bit larger. Pen ink. There we go. So we started up here at the top with uranium. Uranium will decay, and now notice that it's going down by 4. So that would be an alpha decay down to thorium. And then once it does that, it's decaying by beta across, and then an alpha and an alpha and an alpha and another alpha and another alpha. And then it goes beta and beta, and then alpha, and then beta, and then beta, and to lead. Each one of these has a different amount of time that this occurs. I think the total uranium decay series is like 4.3 million years. 4.3 billion, sorry, the age of the Earth, 4.3 billion years, which is insane. But that's why we still have some uranium present. But it does decay. And some of these are super short. I don't think I actually have it with me, dang. But some of them are fractions of a second or just a few seconds. Some of them are years. But I know the entire decay series is crazy long, it's like 4.3 billion years. But this does happen. And you can kind of see what's happening here is that it is changing from to different elements by that decay of, be it alpha, beta, or gamma, or well, gamma's in all of these, but alpha or beta. I could have given off positrons or whatever, but in this particular case, just alpha, beta. Okay, cool. Carbon-14 dating, I briefly spoke about this in class yesterday, kind of again, dependent on the class, but nitrogen in the atmosphere will actually collide with neutrons to produce carbon-14. It does this naturally. And so carbon-14 is produced, depending on when it is in the life cycle of the Earth, it's different amounts, but it gives off a certain percentage of carbon-14. That carbon-14 combines with oxygen to form CO2, and it gets incorporated into plant materials. Those plant materials are then eaten by people, animals, whatever. And so there's kind of a constant replacement of C14. So, but after you die, or after a living organism dies, the carbon-14 starts to decay at a steady rate because you no longer eat. You never take in carbon dioxide anymore. And if that's true, then as that amount goes down, you could calculate how long that substance has been dead or has no longer been taking in CO2 or eating objects that contain that C14. And so what it does is carbon-14 naturally decays to nitrogen-14, which is stable. Here's the decay that takes place. We did this yesterday, but you can find out the age of a fossil by doing that. And they should have discussed this a little bit with you in biology, but of course you may not remember. But there's 2 different ways to do it. One is by finding the percentage of carbon in an organism, and then what it is currently, say, in that fossil and what it should be, and then figuring out how many half-lives have taken place, because the half-life of carbon-14 is 5,730 years. Another way to do it is by the decay rate. So like a current decay rate, I don't really remember what it is, but you could be given what a decay rate is currently, and then what a decay rate of a particular fossil is, and then you could divide that to find how many half-lives have taken place based on the decay rate. It works kind of the same way as just knowing what the percentages are. So here it says, if the carbon-14 sample is only 1/4 of a living organism of the same species, how old is the object? Okay, well, for 1/4, how many half-lives actually took place? 2. So this means 2 half-lives took place, and it's a carbon-14 sample. Well, if it's 2 half-lives, 2 times 57, it's 5730, right? I'm not crazy. Okay, yeah. 5730 is going to be like 11,000, what? 11,460. Is that right? Did I do that right? No. I'm going to show you the answer because I can't math. I forgot my calculator. 11,460. Yeah. 11,460 is the total time that's passed. That's telling you how old that organism is, or how old that fossil is, excuse me. So about 11,460 years. This could, like I said, it could also be done by decay rate. I think we have a couple of those in your homework as well. Just decay, just treat decay rate just like the amount of percent of something that's in there. So if it was 15.6 now and it's what, 7.8, one half-life took place. And so you would multiply it by 5,730 years. So those elements that we talked about before, we're actually going to do more of this later, but you can have a decay series where they actually show you these. We're going to do this later, but all we're really going to do is be balancing them. We're not going to do like the chart. I said this at the beginning, but we'll let that go. I'll kind of quit there. Let's just quit there. So anyway, let's go ahead and quit there. So I'll be back on Monday. If you have questions, great. For the rest of the class, you've got some time. Maybe work on worksheet 2, which is some balancing. Pretty easy stuff, I think. And send me any questions you have over Schoology. Otherwise, I'll see you guys on Monday. Make sure you say bye to Williams.